Good morning. Welcome to another edition of Chemistry on the Fly with Mr. F. Today we're going to talk about 4.10 covalent bonds. Now, there are three types of chemical bonds, and these are things that hold elements together, whether there be molecules or compounds. The first type is going to be covalent bonds, and that's the one we're going to talk about today. The next one is ionic bonds, and then the last one is metallic bonds, and we'll probably talk about that in the next couple days. Okay, so what are covalent bonds? So the first thing we need to do is break down the word covalent. Covalent is going to tell us that the bond is co. Now, co-anything, we have to pay attention to what that is. So co would be like co-teacher, which means that we would, if I had a co-teacher, I would be sharing responsibilities. If there was a co-captain on a hockey team, for instance, they would be sharing the responsibilities of being a captain. So the idea of co means that you're going to share. And in this case, we're going to share valence electrons. Now, another thing with covalent bonds is that they occur between nonmetals. So here's our periodic table, and one of the things we want to realize with our periodic table, we put our nonmetals in yellow. So we're going to get rid of all the other elements. So again, they occur between nonmetals. Now, we're also going to get rid of group 8A. Now, 8A are our noble gases, and they're already pretty happy, so they really don't want to make bonds. So we're going to get rid of those. Now, scientists have been able to make bonds with some of the bigger elements, but that's such a rare occurrence and that's really hard to do that we're not going to consider that. All right, now we're going to review a couple of things, and the first is a rule of 8. Now we're going to add to this one a little bit. So atoms are happy when they have 8 valence electrons. That was the rule of 8. Now we're going to add a little bit to that today. So we're going to say that when an atom has a full outer ring, it's also going to be satisfying the rule of 8 or making happy atoms. We're going to take another look back at our diatomic molecules. Now, diatomic, again, breaking down words, we have di, which means two, and atomic means atoms. So I have 2 atoms. So here's some examples of some diatomic molecules. Now you can notice that the first one, the one on the left, is the same element, and the one on the right can be different elements. So they don't have to exactly be the same element. But this is going to be important to us. Now what we're going to do is we're going to look at the periodic table once again, and we'll see that there are 7 elements in that exist in the diatomic state. And it's kind of interesting, and they happen to all be nonmetals. So here's our nonmetals again, and they are hydrogen, over there. And then I make kind of a 7 on the other side. So I start with nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And if you can see, look at all of these elements, you can see that they have just a 2 after them, which means that they have 2 atoms. So H2, N2, O2, F2, Cl2, Br2, and I2. So those are all my diatomic molecules. Okay, so we're going to look at some examples. Now there we'll find out that those diatomic molecules do form covalent bonds. So we're going to take a look at hydrogen first. So here's our Bohr model for hydrogen. So I have a proton as my nucleus, and I have 1 electron somewhere around the nucleus in the electron cloud. And we're going to, when they bond, hydrogen's not going to doesn't like to sit by itself. Again, the whole idea is to have a full outer ring, and right now neither of them do. Hydrogen can handle 2 atoms or 2 electrons in its outer ring, and it only has 1. So it's going to bond, and oftentimes it bonds with itself, another hydrogen atom, and we get a bond between the 2 atoms. So now both of these atoms are now happy. Now, if we look at the two electrons in the middle, these are shared, which is one of the main characteristics of a covalent bond. And we'll notice now that each of the hydrogen atoms thinks that it has two electrons in its outer shell, and they're going to share those two electrons. And they both think that they're full, so they're both happy. Let's look at the Lewis dot diagrams, and we're going to kind of mix them up a little bit so that we can put them together. So when I put my Lewis dot diagrams together, I'm actually going to be able to put them together like this, and then, just like before, I can show that my two electrons are shared. Okay, we're going to look at a larger atom this time. In fact, it's going to be two atoms, chlorines. So there's two chlorines, and we can see that they have two electrons on their first energy level, 8 on the second energy level, and only 7 on the third energy level. And they're not happy yet because they want to have 8. So they're both going to combine together, just like the hydrogen atoms did. And now they're going to be happy. Why are they happy? Well, let's look. These are our shared electrons, and both of the atoms, the chlorine atoms, think that they have 8 electrons. Let's check this out. So there's 1, 2, 3, 4, 5, 6, 7, and 8. So the left one thinks it has 8. And let's count the other one. 1, 2, 3, 4, 5, 6, 7, and 8. So the right one also thinks that it has 8 electrons. So it is also very happy. Again, we're going to look at our Lewis dot diagrams, the same idea. Okay, we're just going to turn them around a little bit, and then we're going to put them together. There we go. Now they're together, and you can see that both of the chlorine atoms think that they have 8 electrons. The two in the middle, again, are going to be shared. Now, we're going to talk about something a little different today, and I call this pairs and spares. Now, we're going to look at the first, actually it's not the first 8 elements, but we're going to look at one element from each of the A elements, or A groups. So I have hydrogen representing group 1A, beryllium is 2A, boron is 3A, that's our friend from earlier lessons. Carbon's 4A, nitrogen's 5A, oxygen 6A, 7A is fluorine, and neon is 8A. And as you can see, that each, as we go through the different groups, they have that number of valence electrons. So hydrogen was 1A and it has 1, and boron has 3, is in 3A and has 3, and so on. So we can see that. Now, there's a couple of things we want to talk about with pairs and spares, though. So, pairs, it turns out that even in valence electrons, they like to have pairs. And once the side of the Lewis dot diagram's full, we can't get a third one in there. So it's kind of full. It's kind of like no more room in the end, and they're just full, so they don't need anything. So let's look at our pair ones. So the first 4 do not have any pairs. And then we go to nitrogen. Oxygen is going to have 2 pairs. Fluorine is going to have 3 pairs, and then neon, as we'd expect, has 4 pairs. It's a noble guess. It doesn't make bonds with anybody because it's already happy. So neon's already happy. Now let's look at the next part, though. So we go back to hydrogen, and it has 1 spare. Now it turns out that these spares are the ones that are going to bond with other things. So hydrogen has 1, beryllium's going to have 2, boron's going to have 3, carbon's going to have 4, nitrogen is going to have 3, oxygen's going to have 2, fluorine is going to have 1. Now I look at this kind of like parking spaces. So hydrogen has 1 parking space that needs to be full. One part of the side's full, but with 1 electron, but it needs another one to park. Beryllium has 2 parking spots. Carbon has 4 parking spots. So here's our hydrogen again. We saw this a little bit earlier. Okay, so they're going to be coming together. They're both green. Okay, and then once they get to be put two together, they actually become now a pair. And now both of these atoms are happy, which we've already discussed. But we can kind of see that now that once they get together, there's no more space on those sides, and now they're completely full. And just like we said before, if we drew the Bohr model, we would see that the first energy level would then be full for each of the hydrogen atoms. And we did see this before. Now we're going to pick up a brand new term today, and this is called electronegativity. We're going to go back to our periodic table again, and I abbreviate electronegativity because it's a really long word by the letters En. And what this means, it's a measure of how strongly atoms attract electrons to themselves. So I think of electronegativity as strength. So I think of there's an electron, and then there's an arm that steals and holds on to that electron. So that is, again, what elements are going to be able to do that? Okay, and there are some rules that we could follow. Look at our periodic table again and try to figure out who is the strong elements, or who are the strong elements. Now, you can look at the periodic table here. Now, I have it in different colors than we're used to. I start off with the low numbers on the yellow side, so that's the low end of electronegativity, and the yellow, and then you can see some of the blue ones. So mostly the metals are going to be yellow and pretty weak. Okay, then we have some blue ones. Notice hydrogen is blue. And then most of the transition metals are blue, and then we go to the metalloids, they're blue. But as we go up towards fluorine and oxygen and chlorine, they get to be super strong. So fluorine is actually the highest electronegativity. It likes to steal electrons any way that it can. And then oxygen, chlorine, nitrogen, bromine are also elements that really have high electronegativity. And we'll figure out why that's important in a little bit. Actually, we're going to talk a little bit about it now. So we're going to bring in another element or another compound that actually has covalent bonds, and it's our friend water. We all know water is H2O. And so what does that mean? It means I have 2 hydrogens and 1 oxygen. Okay, now my hydrogens have 1 parking spot each, and my oxygens have 2 pairs already, and they also have 2 other parking spots, so they have green lights. So what's going to happen? We're going to have one of our hydrogens is going to go over and combine with the oxygen. And then the other one, we're going to turn this one around and then bring this guy over. And now we have cha-ching, and we have good bonding between them. Now, a couple things to notice. The first thing to notice is that oxygen thinks it has 8 electrons. 2 on the top, 2 on the right, 2 on the bottom, 2 on the left. So it thinks it has, and we're going to realize that these 2 are shared, and these 2 are shared. Now, the challenge with water is that it's not actually shared evenly. Okay, so the electrons are not shared evenly. This goes back to the strength that we had before. Oxygen is much stronger. If you remember, oxygen was a reddish color and hydrogen was blue, which is kind of medium. So we have electrons want to hang out with the oxygen more because it's stronger. So we're going to come up with a new term, and it's called partial charge, and it has a symbol that's kind of weird. It looks kind of like a D, but in fact it's actually a Greek letter for delta, And sometimes you may have seen delta before in the capital form as a triangle. This is actually the lowercase delta, and it stands for partial charge. Now, when oxygen handles or has extra electrons, guess what? It's going to have a partial charge, and it's going to have partial minus charge. So what does that mean? It means that the electrons hang out with the oxygen side of the water molecule more often. And then if there's a partial negative charge on the oxygen side of the water molecule, well, guess what? There's a partial positive charge with the um, hydrogen side of the water molecule. So I like to look at this as strength. Okay, we talked about this before. So here we have water, okay, and I have a strong oxygen, okay. Red, I put a red O in there because it has a high electronegativity. Now I'm not going to worry about the numbers. For now, it doesn't really matter for us. But we're just going to say that oxygen is red and very strong. And then I'm fighting against hydrogen, which is kind of medium, not super weak, but not very strong either. And then here's an electron. And then who's going to win this electron? Well, guess what? It's going to go and hang out with the oxygen much more because it is a stronger element. So this actually has a name when we have compounds that are that have partial charges where one's much stronger than the other, and that term is called, well, there's a partial negative because the oxygen has a negative charge, and a partial positive because there's the poor hydrogen doesn't have any electrons, so he's kind of just a proton all by himself, which is protons are positive. Okay, so there is a name for that, and that's called polar. Now, polar is unequal sharing of electrons. So in this case, the oxygen is going to hold the electron much more often than the hydrogen has. So the hydrogen is going to think, I don't really have an electron. Although I still share it, I might get it only once in a while because oxygen is kind of a hog here, and he takes it and beats me up all the time. Okay? So that's what that one's going to look like. Now let's go back to look at chlorine. Now this one's kind of interesting because we have chlorine on one side and chlorine on the other side, both very strong. And what they end up doing is they end up sharing that electron back and forth and back and forth. Okay, and that actually has a name too, and it's called nonpolar. Now, these are equal sharing of electrons. Now, I want you to remember that polar and nonpolar, they're both sharing their electrons, so they're both still covalent bonds. But in water's case, we had a point where it was unequal sharing of electrons, and in chlorine's case, we have where they're equal strength, we have equal sharing of electrons. Now, that's a whole lot of stuff today. We're going to do a quick review. And so, first of all, covalent bonds share valence electrons, and they occur between non-metals. Pretty basic there. We had the rule of 8. We said atoms are happy with 8 valence electrons, but we did add a little bit more to that today, or they have full outer rings. We talked about pairs and spares. Okay, the hydrogen has one spare, so it has one green light to go and park somewhere. Oxygen has 2 green lights. Fluorine has 1. Carbon has 4. Okay, so we could see that these are all green lights and parking spots that are available. Neon has no parking spots. They have all red lights, all red pairs. So that means that they're already full and there's no need to take on anything else. We talked about electronegativity as a measure of how strong atoms attract electrons to themselves. Okay, and we said who's the strongest. We had fluorine is the strongest on the top right, and then we have francium on the bottom left is the weakest. And we could see the metals, lithium and sodium, and a lot of the metals in group 1A, they're also very weak. Hydrogen's kind of in the middle, and then most of our transition metals are going to be in the middle as well. Okay, we talked about polar, where we had a strong oxygen and a weak hydrogen. Okay, the water solid had a partial negative charge and a partial positive for the hydrogen. That was calling it polar, and it was unequal sharing bonds. And then the last thing we looked at was chlorine, where we were equal strength, and these electrons were being shared back and forth, and that was called nonpolar, where they're equal sharing of electrons. Well, guess what, guys? That's all we've got for today. Thanks for another edition of Chemistry on the Fly with Mr. F. And as always, have a great day. Of cells, then we will be done for today. 8 electrons. So let's take a look. Oxygen has 2 parking spots, fluorine has 1. So we'll kind of go back to our original hydrogen, and we're going to look at how we fill those parking spots.